Okay, I'm ready to start. So can everyone see the screen? All right, we are starting. So far we have covered five labs. So if time permits, we will cover the remaining four labs today. So let's start with experiment 8, that is the genetic algorithm. So implement an algorithm to demonstrate the significance of genetic algorithm. So as problem, per the problem statement, let me give you a brief overview what this problem is about. So we have a population of 20 of 20 people, and what we are doing is we are modifying the every generation we are modifying the population. We can say we are enhancing the population, and not just enhancing any other thing. We are enhancing the fitness index, the fitness value. Only that. Okay. So every past generation there will be a little enhancement in the fitness score, and we are going to find the maximum fit individual, the fittest individual. Okay, so that individual will be denoted in the form of a binary person. Okay, but this is our program to find that after 100 generations, has the fitness increased or not? Has the fitness increased or decreased, whatever that might be? Okay. So, so this is actually an optimization algorithm. So not basically a supervised or non-supervised machine learning algorithm. All right. So let's start. So first we are importing necessary libraries. So you know that without NumPy, the arrays and the many of the functions won't work. So we use NumPy here to apply those matrices, to apply the operations of matrices. And there are many actually functions of this because of this NumPy. And here we are defining the fitness function. So this is the quadratic equation that has been given in your lab. So I've applied that. I actually used other equation also. So it would work for both of the equations. This is just just a quadratic equation. It could be anything. In reality, if we are doing a bigger or complex problem, this could not necessarily be one second order quadratic equation. It could be a much more complex equation, and you could to deduce what the equation could be, that could take quite a lot of effort. Right. So this is where we are defining the fitness function. This will decide what would be the fitness of the individual based on its position. So here we are giving some of the data. We are defining some of the data, like population size is 20, chromosome length is 8. Now length is 8 means what? There will be 8 bits, 8 binary elements, like 1, 0, 0, like that. So that would be the chromosome length. And either it will be 1 or it will be 0. All right. So we know that the chromosome is actually made up of genes. Okay, genes are actually contained in chromosomes. So chromosome here are the 8 that we are seeing, that is 8 genes here. What we are seeing here is 8 genes. So when we are going to iterate through the chromosome, we will see that we in every iteration we get one gene. Okay, that is the problem for later. All right. So this is the mutation rate. You will know what actually it's the significance of it. That is, mutation means what is the enhancement? Basically that. What is the enhancement we are having? How are we enhancing our gene? That is what we are going to do. And this is the number of generations. So we are talking about 100 generations. So after 100 generations, we are going to calculate, okay, what has happened to the fitness of the individuals. Not all individuals, perhaps, but how is the fittest individual? What is the fitness score of the fittest individual? Right now, we are doing this binary chromosome to decimal value. So usually it is decimal, but we are supposed to sometimes convert it into binary. Sorry, Usually it is binary. We are supposed to sometimes convert it into decimal for some operations. So we'll see. Okay. So let's now initialize the population. So let me list it. So here you can see that this is the population. These are 20 people, and they are all denoted by binary numbers. So here I'm actually printing the fitness value of present individuals, not all individual, but the maximum fit person. So this is the I will just run this. So this is the maximum value so far found for particular the the fittest individual is has the fitness score of 63,758, and this is the maximum fit individual. All right. Now this is where we are going to run the genetic algorithm. So pay attention on this one. Okay. So we are going to iterate through the number of generations. So we'll run 100 iterations, we know that. And one iteration is one generation. Now, as we said that we are going to, calculate the fitness values because of this fitness function. And here we are, this binary to decimal is going to come in handy. Now, we are going to convert this individual, which is actually a binary number right now. So we are going to convert it into decimal, and then we are going to calculate the fitness through the fitness function, its fitness value. So right now what you're seeing here is a list comprehension. So all those, so for individual in population, it will take one individual, it will convert that individual's binary score to decimal score, and then it will apply a fitness function on that. After doing that, after doing that, you get the fitness value of that individual that you will append to the list. Okay. And it will do that for all 20 people because our population size is 20, right? So this is the list comprehension that does it in one line. Otherwise we'll have to run a loop and then we'll have to append to the fitness function. So sorry, the fitness value. Okay. Initializing it as an empty list and everything. So we're not doing that, we're doing that in one line through list comprehension. Now here we are selecting parents for this using tournament selection. Okay, so what is tournament here? Three individuals will be taken randomly, and the best of them will be selected as a parent, and it will be he will be appended to the population as a winner. Okay, so right now let's get into this. So we'll uh, right now what we'll do, we will iterate through the population size and we'll find what are the tournament indices. So in tournament indices, we will find the, you know, the indexes of those people we are actually selecting. So let's say we are selecting 1, 3, and 5. The position was 1, 3, and 5. So 1, 3, and 5 are selected. So now then we will actually, you know, now then we will actually do what? We'll actually calculate the fitness level of the fitness value of all those three people. Okay, now we have that in a list. Now we'll find the winner index. How will find the winner index? Nothing, but the maximum. We'll find the maximum value of that tournament fitness. So what is the maximum value? We'll find that, and then we'll take what is actually the index of that one. What is actually the index of that winner? Okay, then that will copy in winner index and winner index. So now we have the index, right? We have the whole list and now we have the index of the winner. So how will find the winner? Population of winner index. Okay, that is how we do it, right? So this is a list and this is the index. How you find a particular individual? Population of winner index. There you got a winner of the tournament. Now that will go on again and again. So once, okay, so again and again it will go. So now we have found parents. Okay, now we have found parents. We are deciding the next generation, right? So now we have found parents, and now we will do what? We will actually, now we have this selected parents. In this selected parents, there are all parents right now. So now we have to produce a next generation. So how will that happen? We'll take that in an empty list and we'll iterate through the population size. And you're seeing the step two here. Why actually we are seeing step two here? Because two people are required. Okay, one male and one female. So it is being considered here that the male and female are adjacent. Okay, so male and female has been taken, and they have been selected as they have been taken as selected parents I of one. As I said, adjacent. All right. So now we are taking crossover point. Now let me tell you what is crossover point here. We know that our chromosome length is 1 to 8. Okay. So it will take one point and it will say, okay, this is a crossover point, and here I will divide the genes. Okay. So let's say I'm creating two children only. Okay. So we have some standards to make this program a little simple. Okay. So we are creating two children out of two parents. So we are not actually increasing the population. It remains 20 on every generation. Okay. Now, child one, child two, we are creating, and we are using crossover point for this. So let's say what actually is crossover points. So this is a chromosome, let's say. So don't go on reading all this, what it is. Let's say it is divided into 8 genes. Okay. So I am taking any index of a gene. Let's say I've taken third. Okay. I've taken third gene and I've made it a crossover point. Okay. Now let's say I've taken a third gene and I've made it a crossover point. So our first child is taking first 3 genes of one parent and last 3 genes of the second parent. Okay. Understood. So the first child is taking first 3 genes of the first parent and last 5 genes of the second parent. Now we have created one child. Second child will do just the opposite because we are taking only one crossover point. Okay, and we are taking it as a random at random. All things we are doing at random. So the second child, what it is doing just the opposite. It is taking first 5 genes of the first parent and it is taking sorry. So it is taking this, yeah, yeah. So first 5 genes of the second parent and first 3 genes of the first parent. So 5 genes of second parent, that is actually just write some number here so that we can understand what, let's say it is 3. It is, now I'll get. Okay. So every one of us knows indexing, right? So when we do this indexing, what do we get here? We get 0, 1, and 2, right? That is what we get. 0, 1, and 2. That means we are getting the first 3 indexes of parent one. Means first 3 genes of parent. Here what we get? We are getting from 3 to the end. So whatever is remaining, that means 5 genes are remaining, right? So 5 genes we are taking from parent. Okay. And we're doing the exact opposite in this. So what we are doing, we're taking first 3 genes from parent 2 in second child and this 5 genes means last 5 genes of first parent. Okay. That is how we are creating child 2. How child 1 is created? First three genes of parent 1, last five genes of parent 2. How second child is created? First three genes of parent 2 and last five genes of parent 1. So you can write it in any way, but for our understanding, making the program a little easier, not making it complex, I've taken only one crossover point, and that's how our we are getting our children. Okay, so next generation dot extend. So since I'm taking it as a list, I'm using extend, and that is appended. The two elements are appended to that list. Now it becomes two, and it runs for 10 iterations, right? Because we have a step of two, right? So now in 10 iterations, 20 people are actually appended to the population. So how that will happen? Let's see. Okay, next generation contains 20 people now. Okay, now let's perform the mutation. How will be the next generation better than the previous generation? Okay, so for I in range population size, yes, 20 it is. So now for J in range chromosome length, now we are altering every gene. And what is gene? The particular binary elements of a chromosome. Okay. Particular binary elements of a chromosome. What was chromosome? That was 8-bit. It is uh, where have we defined the chromosome? Here we have said that the chromosome is 8. Okay. Here we are saying that chromosome length is 8, and we are supposed to do what? We are supposed to check what is actually, so whatever in next generation, that all of them, here you can see that all of them have 8 bits of binary. Okay, 8 binary elements, you can say. Okay, in 00004 times, and that will be size of 8, right? So all of them will be altered. We are iterating through every single one of them through this chromosome length. The length of it is 8. So now it is just checking at random. Okay, so we don't have any supporting data, so we are just taking random. So np.random.rand, if it is less than mutation rate, and what is mutation rate? 0.01. So it will convert it will take a decimal number, and that is why it is creating every time a different result, because every time we are getting a different random number here. Okay, so it will do that. So and np.random.rand less than mutation rate, next generation of ij is equal to 1 minus next generation of ij. So what will happen? So if it is 0, it becomes 1. 1 minus 0, it becomes 1. If it is 1, 1 minus 1, it becomes 0. So we introduce mutation in offspring. We iterate through each bit in chromosome, and with the certain probability, flip the bit. So we are just flipping the bit. We're doing nothing else. Okay. So update the population. So now we are updating the population, and what happens is here, what is happening here? Population dot is equal to np dot array next generation. So now we have a new population. Okay, it is the first generation. From the first generation, we got a new population. Okay, so now again it goes to the next iteration, and it will create a newer generation. Every time it creates a newer generation. Okay, so in the 100th generation, we will have the 100th generation with totally altered chromosomes. Okay, so now we have some. So let me actually do one thing. Let me print the population now. This population is actually, the 100 ginger population of the 100th generation. Okay, you can see this. Most of them has 1 1 1 1 1. All are altered. Okay, so here we are doing the same thing. Fitness, we are taking the fitness values. Okay, again in a list through list comprehension, and then we are finding, we already did this, right? Then we are finding the maximum fitness index, and then we are finding the value. So rest of this is just not it. Then we are finding this, then we are doing this. So this is our maximum value found. That is, this is the fitness quotient now. What was before? It was 63,000 something. So we can deduce that, okay, the fitness through the 100 generation has been increased. We can say that. Okay. So that concludes our genetic algorithm. So it can happen that, when you actually do this problem to a larger data set, the logic will be the same, but you will have to you will have to actually use a larger amount of data and realistic data. So some changes would be required, but the logic would be the same. So now we are done with that. We'll move on to the easier problems. Okay, let me take care of first this Bayes theorem. Okay, before that, as anyone, any questions? Are there any questions? If there is no questions, then we will, there are no questions, we will move on to the next one. All right, take that, there are no questions. Okay. So now let's see what Bayes theorem is. So Bayes theorem says nothing that if we have a prior probability, we are assuming something. That means we have some kind of prior guess. Then we get a new evidence. Then we edit our guess and we make a new guess. Okay, simple way to explain this, and we do that in a mathematical format. So what I said is just theory. So let's say I'm saying in theory, okay, so it is going to rain tomorrow. The initial, that is the initial wave is called prior probability. Now I receive new information like weather forecast. That is called evidence. Now based on that evidence, I will add that to my prior probability, and I will say whether that will be a sunny day or where there will be with rain, there will be storms too. Okay. Now that concludes our, that actually creates our posterior probability, and that posterior probability will be the final value. That is what we are actually going to deduce. Okay. So Bayes theorem helps us update our beliefs of probabilities based on new evidence, nothing else. So let's say now we are taking actually a problem that the student is absent and the today is Friday, and probability that today is Friday given that a student is absent. Okay, so we are getting that there is 3% probability that the student is absent, and there is 20% probability that today is Friday. But now probability that today is Friday given that the student is absent. That means if a student is absent, the probability of today being Friday is 100%. That means what? A student always gets absent on Friday only. He will not take any absence any other day. So that is what it is saying. That means that if a student is absent, there has to be Friday. What we have to calculate alternatively is what are the chances that the student is absent, what are the chances that if it is Friday, a student is absent. So a student takes leave on Friday, but he does not take leave on every Friday. So if I'm saying that today is Friday, what is the probability of that student being absent? That is what I'm going to do. Okay, let's say you are a student and there are 8 weeks of your course and you take leave only on Friday. You have to go meet some. All right. All right. So that you go on Friday, but you don't go on every Friday. So the professor in your class can say this student will be absent. If he will be absent, he will, otherwise you're regular in the class. So this student professor says this student will be absent only on Fridays. Okay, but not all Fridays. So he can say that, okay, if it's the person absent, that it means it's a Friday. We are certain of that, but we are not certain which Friday. So we have to calculate the probability right now. Okay, so based on the probability of the absence and based on the probability of what the probability of Friday is. Okay, so now we are going to apply Bayes rule. Okay. PA given B. So this is what we are actually trying to find. PB given A is 1.0. Okay, and probability of A is 0.03. Probability of B is in it being a Friday, and this is the probability of absence or being Friday is means a student is absent and it is Friday. It is 1.0. That means 100. Running this and then this, and I'm printing the result. That is 15%. So I took an example of 4 weeks. That is, or was actually shouldn't have taken that example because we are talking about 0.2. So actually, we might be talking. We are talking about 5 working days. Okay, that means Monday to Friday. That is why the probability of being Friday is 0.2. Okay, so that is what it is. That was just to give you an example. Okay, but you get the picture, I guess. Are there any questions? So let's explain this in a different way of explanation. That's okay. So this is our bias theorem because we talked about what? We talked about posterior probability, we talked about prior probability. Okay. So this is our prior probability that the student is absent. That is what we guessed. Likelihood is one, probability that today is Friday, given that the student is absent. That is one probability. Okay, that is the likelihood. Marginal likelihood is that today is Friday. Now, based on all that, I'm going to calculate posterior probability. So it is doing the same thing. It is applying the same formula. Plus, I'm giving it in a form of posterior and prior. Okay. So that will conclude our bias theorem. Are there any questions? So we'll move on to the next experiment. So experiment 1 and 8 has been taken care of. Let's move on to this experiment 5, which is finding probability of credit volumes. So here we have actually around 10 individuals. So there's a little mistake in this the document that has been given in this. There are not 8 training examples, there are 10 training examples, and count of goals occurrences is 4. Okay. So this is how the data set is, the row and column. Let me refer it to this. So what it is actually income, recreation, job status, age group, homeowner. So let's say a credit card company is taking this data that okay, income is medium, this is his recreation, this is his job, and this is his marital status, this is his age group, and this is whether he is homeowner or not. Based on all that, they have created one thing that is high risk. Okay. Now we are not going to calculate how they have actually created, but this is the label data. Okay. So these are all these parameters they have created high risk. They have said, okay, this is the high risk. We just have to calculate the probabilities of something. Probabilities of what? Now this is our data that we have. We just have to calculate the probabilities of, first of all, unconditional probability of goal. Okay, how many golf players are there? Okay, what would be the probability of a person being a golf player? So what we'll do, because it's an unconditional probability, right? So first of all, we'll say what is the length of the data set? That is 10. First, we'll run this many sessions. So we can see that total examples, total data set is actually 10 people, and we are counting goals. So some one, for example, so it is, this is also for example, and you can, if you want, I can, write like this. Sum is equal to 0. Then for I in, yeah, for, for I in data set, golf in I, sum plus equal to 1. Okay, so that is what it is doing. Okay, instead of I, it is taken example, just that. Okay, want to see, let me, okay. So same thing, right? Just a faster way of writing code. That is what it is. My misunderstanding. So after we are getting here, there are four occurrences of wolf. That is what we were actually calculating. Okay. So now we are going to count the occurrences of single given matrix. That is what the question is, right? First, calculate the unconventional probability of golf and the conditional probability of single given matrix in the data set. So single and medium risk. We have to calculate the probability of that, right? So first of all, what we'll do is count single and medium risk. So what it is doing, it is checking if single is an example and matrix is also an example. So it is checking whether, first it is checking, let's say matrix. Okay, how many matrices are there here? Matrix, three matrices are there. Out of those three matrices, how many are single? Two are single. Okay, so we have got, okay, this is our count single matrix. So two out of three, we can see. Now we calculate the probability. let's our single in I and measure risk by two conditions. And one. Okay. Same way we'll do for the matrix two. Okay. Only difference will be so first one is three, two, and this is three. Let's calculate the probabilities. Okay. So probability of golf, that is end conditional probability, count golf upon total examples. And single given matrix is count single matrix and count of matrix. So we have already calculated those, right? 4 by 10, that is 0.4, and 2 by 3, that is 0.666. If you are going to calculate, okay, how many in the whole data set, what is the probability in whole data set that we can get the individuals who are also single and are having this matrix, so you can only do this also single and have been given medium risk by the credit card company or any company. So you can say 2 by 10, that is 20%. So that will conclude our conditional probabilities, conditional and conditional probabilities. So that is will conclude our experiment 5. So let's move on to the next. If there are no questions, if there are any questions, you can ask. So let's say there are no questions, then we'll move on to the next lab. What is the next lab? That is experiment 4. That is, so given the following data, which is specify classification for 9 combinations of var1 and var2, predict a classification for a case where var1 is equal to 0.906 and var2 is equal to 0.606. Using the result of k-means clustering with k-means. So you must have seen this in then we have given the labeled data here, var1, var2, and class. We don't actually need that. So since we are creating three centroids ourselves because of this k-means, so k-means clustering is a unsupervised machine learning algorithm, so which doesn't need any label data. So you get us give a set of data, let's say coordinates. It will create a groups of those data. It will create, let's say, three separate group of the data that we'll have to give what will be the value of k. You are giving three centroids. So it will create three groups of data. You will give four, so it might create four. You give two, it might create two. Okay. So right now, since we are giving here three centroids, that will be then it will the whole all the data will be divided in three groups. Okay, so we don't need this class here. Okay, so let's move on to this. How we'll actually proceed this. So first, as you know, that we need to import necessary libraries. So NumPy, as you know, why we do it. And here through sklearn, we dot cluster, we will import k-means. So it is very important for you to know that it's easy for me to import k-means and sklearn and anyway, because I'm using Google Colab. If you are using VS Code, then you'll have to first install the sklearn. Then you will be able to do all those things. Without installing Matplotlib or sklearn, you won't be able to do these operations. So make sure if you're working on your VS Code on or Sublime text anywhere, import these libraries, or you can just use this Google Colab, and you can later, if you want, um, that you want the Python file, you can download it as a .py file. Okay. So we are importing three libraries. Why we use matplotlib to plot? Actually, you can when we are plotting a data. So it is an important part of machine learning or a data analysis, you can say, to actually visualize that data. So for our confirmation, okay, whether our algorithm is working properly, and it gives us a good feeling, okay, yes, it is working, and we can see that. So that is why we are using this. And also, if you are going to actually take machine learning on a higher level and you're going to handle big files, then you will see how important our matplotlib and plt is. When we plot that data, we are able to take decisions based on that plotting. Okay. And also heat map and everything. Okay, so you make the decisions based on. So here is our data. We don't actually need 011 that I said, we will extract. So here what we're doing, we are doing feature extraction. So since we don't need 0111, so we'll do feature extractions and we'll print the features, right? So here we are getting all these data. So they are nothing but the coordinates. Okay, we have 9 points on a coordinate two-dimensional space. Okay, so now what we are doing, we initialize the k-means algorithm with three clusters. Okay, we are taking three clusters here to fit it to the extracted features. How we'll do this? We'll do this with this library, by this library. Okay, k means because we have here imported it here from sklearn.cluster import k means. So it says that okay, for clustering we are importing k means. So k means clustering means what? Clustering means just grouping. Okay, so k means clustering means we are grouping our data since we are given three groups here. So in three groups. Okay, now we are calculating centroids. Now if there is a group, there has to be a center of that group, right? So that is what we call here centroid. Okay. So k means dot cluster centers, cluster labels, and these will be the cluster labels. So first I'm printing cluster labels, then centroids. So these are the cluster labels. Okay, see there will be 9. So all these points, because of the training, because I have fit that data. Okay, the main algo has run. I have fit that data and that has been divided into three groups. And you can now see each of these coordinates now belong to a certain group. This belongs to the first coordinate belongs to the second group. The second coordinate belongs to the zeroth group, and so and on and on. Okay. So now here now we see centroids. Now centroid means x coordinate and y coordinate. Now, if there are three groups, they have to be three coordinates, right? Three centroids, right? So that is what we have. So now, when we have done that, this is what our experiment says, that we have to take a new variable, sorry, a new value, let's say a new point, and then we have to predict that where will that point lie. So here we are taking one point and we are predicting where will that point lie. Okay, so let's do that. Get this. Let's do that. New case is equal to np dot array. This. So this is our new case. We can even change that. That will be our cluster 1, not cluster 0, not cluster 2, but cluster 1. Let's change this. Okay, let it be 0.6. Now, I've given some drastic change. Now it moves to cluster 2. Okay, so this is where we predict what will be the cluster. We take a new case. That means our algorithm is successful. Okay, now we're just getting some indices and predicted as classes. So here we are actually finding the class label means the cluster with the highest count. And what is that actually? That is one. Now let's see the plotting. Okay, these are just to predict what will be the what will contain the maximum number of the elements. Okay. Let's plot. Now let's see. Seeing these are the centroids. Okay, and these are the points. So how many of them are in? Four or eight, so nine. So 9 point we had, right? We had 9 point. So what? How are we doing it? First of all, we are deciding what will be the size of the plot figure, and then we are going to plot data points. Data I of 0, I of 1, and then cluster labels. Then we are giving some colors and everything. Okay, and then we are going to plot the centroids. So these are just naming it. Because of this plot legend, I yesterday also I told that it will give you some kind of notation. So this is done. So let's plot a new. Let's plot the new case. We had new case, right? So how we'll do that? First of all, we'll plot the data point same way as we did. Now we are going to plot the new case. Here t dot is scatter new case 0 of 0, new case 0 of 1. Okay, and we are giving it an orange color and marking it as a star. Now this is the new case. Initial centroids. We are just naming the centroids as initial centroids, nothing else. So now, run this. See now, this is the new case, and I think it belongs to this group, right? Which group? 0, 1, 2. So it might be one. This might be one group. So, but we don't know, right? Right now, we don't know anything. So why not enhance it a little bit? So in this, what we will do? Cluster same, predicted cluster. K means predict new case. Fine. Okay. So here we are going to mark every centroid, whether it is one or two or three, and we are making it as red. Okay. So that there is some difference. So red it is already, or we already did it, red or orange. And now we are actually marking it through this I plus one and everything. Okay. So it is one, two, and three. So one, two, and three means what? Zero, one, and two. So let me make it actually I, not I plus one. Otherwise, you like. So this is the zeroth group. This is the first group, and this is the second. So we plotted it like that. Now you can see this is the new case, and it is saying that it belongs to cluster two. And if I don't give that, then again there will be a little bit of confusion. Cluster two. It is saying cluster two because I guess it shouldn't say cluster two, because we are saying that the group is 0, 1, and 2. We say that it belongs to cluster 1. Okay, a little bit more enhancement what we will do. We are going to give different cluster colors to every cluster. Now everything will be clear. See now, this is the new case. It belongs to. Now we are actually saying this as a cluster 1, 2, and 3. So new beings belong to cluster 2. That means that if we are considering 0, 1, 2, then cluster 1. Let me just make it a little bit. Change it a little, otherwise, nucleus cluster 1. So centroid 0, centroid 1, and centroid. So now we have this new case in this. Now we have this new case in centroid 1, means the first group. Now we can clearly see. Similarly, if you want, you can create a new case to check any, you can take any point and you can check whether in which group it will be available. It will be there. How will be the grouping be done? Okay. So that will conclude our K-means cluster. Is there any question, any confusion, anything that you have not got? So I think that will conclude all our 9 labs. Yes. Thank you very much. I'm stopping my screen. Hello, sir. All right. So I'm leaving the meeting. I think. Thank you, guys.